Welcome to the discussion on this electronic spectroscopy. Structure of atoms. As we all know that atoms consist of the central positively charged nucleus, and this nucleus contributed almost all the mass of the system, which is surrounded by the negatively charged electron, and the number of electrons are sufficiently balance the nuclear charge. We begin with the central operator of the system, which is known as the Hamiltonian operator. It is denoted with the capital letter of H with a hat. The Hamiltonian operator consists of the quantum mechanical representation for the kinetic energy and also the potential energy in a system. This operator is a mathematical functions which is a piece of differential equations, and it operates on the wave functions given the symbol of psi, which is used to describe the energy state of a system. The equation is a fundamental to understand the electronic structure of the atom. By solving it, we determine three key things. Number one is that the way electrons group themselves about a nucleus when forming an atom. Number two is that we are able to find out the specific energy which an electron may have, and the way in which an electron can undergo transitions between different energy states. The solution of this Hamiltonian equation gives us the wave functions psi, along with some appropriate quantum numbers. The wave functions themselves are complex mathematical expressions that consist of three main components, some which involve some fundamental physical constant such as the Planck constant speed of light, the coordinates of the system, and some appropriate quantum numbers. This is the general form of the wave function, which consists of the radial part and also the angular part. For a complete description of the electron, we must account for the spin. So spin is another part of the total wave function that comes from the solutions of the direct equations. Therefore, the total wave function for a single electron is often referred to as hydrogen light atom, is a product of the spatial part and also the spin part. When this quantum theory is applied to electrons, the theory uses the wave functions to predict the probability of finding an electron with a particular energy at a specific point in space. This probability is measured as the relative probability density. The probability of finding an electron within a unit volume at a particular point in the space is proportional to the square of the wave function. The effective boundary that defines the electron's domain based on this probability is called orbital. Focusing on the one electron atom, the solution of the Schrödinger equation for radial component helps us to define the key parameters. In these expressions for radial part, R represents the radial distance of the electron from the nucleus. The solutions also depends on n, which is the principal quantum number. The principal quantum number can have integral number or integral value of 1, 2, 3 or infinity. As we saw earlier, the general form of wave function is given by these expressions. that the wave function is a combination of the radial and also the angular parts. The complexity of these mathematical expressions is what allows us to define the precise shape and location of an electron's domain. To completely specify the electronic wave functions of all atoms, we require the introduction of four quantum numbers n, l, m or ml, and s or ms. Based on the quantum mechanical description, we can define an atomic orbital as a one-electron wave function for an electron in an atom. When an electron is characterized by one of these specific wave functions, we say that it occupies that orbital. For example, if an electron is described by the wave function of psi subscript 1, 0, 0, or the state given written in this manner, it is said that the electron occupies this orbital where the quantum number are n equals to 1, l equals to 0, and ml equals to 0. Just now you have seen the different types of quantum number. This table summarizes the quantum number involved in labeling the electron in an orbital. So we have the principal quantum number given the symbol of n, which will govern the size and also the energy of an orbital. The value of n range from positive integer to infinity, whereby the value of the orbital angular momentum quantum number is given with the symbol of L, lowercase letter, and the value is ranged from n minus 1. So this will govern the shape of the orbital, while the directions of the orbital angular momentum is given by the symbol of ml or L subscript z. So this will govern the directions of the angular momentum for the orbital. Their values range from plus L to minus L. After that, we have the spin for the electron. So we have the spin quantum number S. The value of the S is 1 over 2. And this will govern the axial angular momentum of the electron. And lastly, we have the spin component on the z-axis, given the label of Sz or Ms. So this spin can only assume certain orientations relative to the z-axis in the spin vector space. The value is ranged from plus 1 over 2 to minus 1 over 2. Now you can see the different shape and also the size of the orbital. We have the 1s orbital, which is a sphere, and then we have the p orbital with the principal quantum number n equals to 2, and the L value, which is equals to 1, and the Lz value is ranged from plus 1 to minus 1. So it has the value of plus 1, 0, and minus 1, which is corresponding to the px, py, and also the pz orbital. So similar to the d orbital, which has the principal quantum number equals to 3, so n equals to 3, and then the value of L is ranged from plus 2 to minus 2. Therefore, it has the value of plus 2, plus 1, 0, minus 1, and minus 2. Therefore, it has 5 different types of the orbital d due to the variations in the Lz. When considering the energy of atomic orbitals, there are two main contributions. Number one is from the attraction between the electron and nucleus. The second will involve the repulsion between the electrons. So if we only focus on the hydrogen atom type of spectrum, or we call it as the hydrogenic atom, where only one electron is involved, then we can ignore the factor number 2, which is the repulsion between the electrons. Besides, due to the absence of inter-electronic effects, all orbitals with the same n value will have the same energy in the hydrogen atom or hydrogenic atom. The energy of the atomic orbital can be determined using these expressions. So we have the energy at different energy level, or the principal quantum number, n, equals to this bunch of the constant multiply the z square, the charge of the molecule, divided by the square of the principal quantum number. The whole bunch of the constant here can be labeled with the symbol of R subscript H, or known as the Ribert constant. The Ribert constant in the units of wave number is equals to Hc multiply the Ribert constant equals to these expressions here, the piece of the constants. Now we can substitute the value of this principal quantum number n equals to 1 to 3 into the equations to determine the respective value of energy for each level. So we can illustrate the energy levels of n hydrogen atoms using the diagram here. We substitute n equals to 1, then we will get this value of the energy at n equals to 1 energy level. And when n equals to 2, this is the respective energy. N equals to 3, here is the respective energy, and so on. Okay, so this set of the energy levels are quantized by the principal quantum number. It has the fixed value, which is determined by the principal quantum number. The total energy from n equals to 1 until infinity is known as the ionization energy. After the electron being ejected from the system, then the energy will become continuum. It is a continuous energy, which is unable to differentiate. From the same energy levels, the most stable state is the energy with n equals to 1. It has the lowest energy, and the value is negative Hc multiply the Ribert constant wave number. And just now I mentioned about the ionization energy. So the atom is ionized when the electron has been excited to the level corresponding to n equals to infinity. So the range of the energy from n equals to 1 until n infinity is known as the ionization energy, or we call it the minimum energy required to remove an electron from the atom in its ground state to the positions which is very far from the nucleus. And the energy must be supplied to the system for the process of ionization to occur. And this value of energy is around 13.6 electron volt for the hydrogen atom. Picture and spectra of hydrogenic atom. Hydrogenic atoms are the atom with single electron in the orbital. Other than the atom, we also have some ions which consist only single electron. For example, the ions listed here. So when an electron discharge is passed through the gaseous hydrogen, these hydrogen molecules will be dissociated, and the energetically excited hydrogen atom, it will emit radiations in the discrete frequency and produce a spectrum with a series of lines. The frequencies of the lines observed in the spectrum can be determined using the equations given here, where the n value is the value of the energy state, n1 is the lower energy state, and n2 is the higher energy state. RH is the Ribert constant. So the positions of the spectral lines appear in the spectrum can be determined using the equations given in this expression. The spectral line will be produced in emission if the electron transit from state N2 to N1. While the selection rule for the transitions are the change of the principal quantum number can be any, whereby the change of the angular momentum quantum number is limited to 1. Therefore, the transitions between levels give rise to the Lyman series if the transitions involve the principal quantum number equals to 1 or arising from the n equals to 1. For the Balmer series, it will involve n equals to 2, and the Paschen series will involve the transitions of n equals to 3. This figure shows the possible electronic transitions of hydrogen atom, which giving rise to the various series in the spectrum. If those transitions involve n equals to 1 to any of the n, then they will need to absorb the amount of energy in the radiations of UV region. While for the transitions involve the n equals to 2, then the value of the energy required is 4 in the visible region. So the electron will absorb the energy in the visible region, and the electron in the N2 will be excited to the other principal quantum level, or from other quantum level drop into the n equals to 2 and results in the spectral lines where it is called the Balmer series. So similarly, for the transitions involve n equals to 3, then the spectral lines is known as the Paschen series, whereby the radiations involved in these transitions is in the region of IR. The spectrum of atomic hydrogen is something similar to this one. It is produced when light from hydrogen gas discharge tube is passed through a prism. The light is split into 4 visible lines. So each of these spectral lines correspond to a different electronic transitions from a higher energy level or higher energy state to a lower energy state. In this region here, you will see that the spectral line involve a higher energy in the region of UV. The principal quantum level involved, or the principal quantum number, is equals to 1. So this series of line is known as the Lyman series. After that, we have the quantum state of n equals to 2. Then it will involve the transitions between N2 to N3, N2 to N4, and so on. And this will involve the radiations in the region of visible. After that, we have the transitions involve n equals to 3, where the radiations involved is in the IR region. However, the Schrödinger equations, it does not take into considerations of the angular momentum and also the spin coupling effect of the electron. It also shows the presence of the single line in the spectrum. The spectral line we have seen just now, in this spectrum here, it involved the transitions from N2 to N1. So the atoms emit radiations upon reverse to the n equals to 1 state, and the radiations emitted is captured by the detector, and it appears as a single line. If the equipment is able to resolve this spectral line, instead of the single line that will appear in the spectrum here, in fact, the spectral line will consist of 2 very closely spaced lines. So what is the reason that from this single line, when we have the high resolutions image or the spectrum, then it will appear, or it will have 2 lines to presence in the spectrum. Before we answer the questions, let's look into some of the spectroscopic terms, which involve how does the electron arrange in the orbiter. If you are given the electron configurations of 2p2, so you know that the principal quantum number n is equals to 2. But these configurations, it does not provide all the informations. It does not contain angular or the spin configurations of the electron. For the angular configurations, it involves the angular momentum quantum number with reference to the z-axis. So we have the Lz. The Lz for n equals to 2 can be either 1, -1, or 0, whereby the spin of the electron, it can be plus 1/2 or minus 1/2. If we arrange two electrons in this orbiter, then they will have many possibilities for the electron to occupy this orbiter. Okay, so for example, if we have the p orbiter with different Lz, we have the Lz equals to +1, 0, and -1. And these two electrons can both arrange in the manner of spin up. So spin up for electron 1, spin up for electron 2. Other than this, the electron also can arrange in +1 orbiter and -1 orbiter with spin up. Or the electron can arrange in this manner, +1 for both electrons, one spin up and one spin down. So the different way that the electron occupied the orbiter is known as the microstates, or these configurations are known as the microstates. Each microstate represents a possible electron configurations, or possible combinations of Lz and Sz. Okay, Lz is the angular momentum quantum number with reference to the z-axis, whereby Sz is the spin quantum number with reference to the z-axis. And the energy of each of these microstates can be varied due to the interelectronic repulsion. So just now you have seen three different types of the arrangement, three different types of configurations, or three different microstates. Each of these microstates will have different energy due to the different repulsions or the interelectronic repulsions experienced by the electron. Those microstates which has the same energy will be grouped under one term, which is called the term symbol. The term symbol consists of three parts. First one is the superscript part, which is known as the multiplicity. It involves the spin quantum number in determinations of the multiplicity. So multiplicity equals to 2s plus 1. S is the spin quantum number for the total spin angular momentum, whereby the x is the total orbital angular momentum quantum number. It is given by the symbol of capital letter L. The capital letter L can have the value of 0, and it is represented by the symbol of capital letter S. If L equals to 1, then we use the capital letter P to represent the X. If L equals to 2, then we use the capital letter D to represent the X, and so on, whereby the subscript J is known as the total electronic angular momentum quantum number. The total electronic angular momentum quantum number J arises due to the effect of spin-orbit coupling. When the electron is orbiting the nucleus, so the electron will have the orbital angular momentum, and at the same time, the electron will also spin on its own axis. So electron has a charge of -1. When charge spinning, magnetic field will be generated. And similarly, just now, when the electron is orbiting the nucleus, it will also generate the magnetic field. The interaction of the spin magnetic moment with the magnetic field due to the orbital angular momentum is called the spin-orbit coupling. And this strength of the coupling and its effects on the energy level will depend on the relative orientations of the spin and orbital magnetic moments. Therefore, it is also depends on the relative orientations of the two angular momentum. The spin-orbit coupling effect will very much depend on the size of the atom. The larger the size of the atom, the stronger is the coupling effect. The strength of the spin-orbit coupling will also depend on the orientations for the angular momentum for the orbiter as well as for the spin. So when the angular momentums are parallel, as in this figure here, the magnetic moments are aligned unfavorably. However, when they are opposed each other, then the interaction is favorable. This magnetic coupling is the cause of the splitting of a term into levels. The total electronic angular momentum can be quantified, which involve the spin and orbital angular momentum. When these two are combined, then it gives us the total electronic angular momentum, J. The operator of total electronic angular momentum operate on the wave functions. It gives us the solutions of Jj plus 1 multiply h over 2 pi square multiply the wave function itself. So the solutions of these equations or the operator for this total electronic angular momentum on the wave functions give us the magnitude for the total electronic angular momentum, which is the bold letter of J. So the magnitude is equals to square root J plus 1, with the J here is referring to the total electronic angular momentum quantum number, and it is written as italic J. The italic J can be calculated from the orbital angular momentum quantum number L plus spin quantum number S. Their value for J is range from L plus S until L minus S with the modulus. So it needs to be the positive integer. In addition to the total electronic angular momentum, we know that angular momentum is a vector quantity, so it also has the directions in addition to the magnitude. So we quantified it with reference to the z-axis, or we find out the component of the total electronic angular momentum with reference to z-axis, and given the value of Jz for the magnitude equals to italic Jz multiply h over 2 pi, whereby h over 2 pi is the unit for the angular momentum. Therefore, the magnitude of the angular momentum or the total electronic angular momentum is depends, or we say that it is quantized by the total electronic angular momentum quantum number Jz, where the Jz is ranged from plus J until minus J. Now let's look into the example with one electron in the p orbital with the principal quantum number of n. So how to derive the term symbols, which is given as the standard format here. With one electron in p orbital, we have the orbital angular momentum quantum number L equals to 1, and one electron corresponding to the spin quantum number equals to 1 over 2. In order to find out the multiplicity, we apply the equations of 2s plus 1. So 2 times 1 over 2 plus 1 equals to 2, and this value will have the effect on the degeneracy. Then we have to look into the possible value of Lz and Sz in order to determine the value of J. So L equals to 1, therefore the value of Lz, which is the angular momentum quantum number with reference to the z-axis will be the value of +1, 0, and -1, while the s is equals to 1 over 2, therefore sz equals to +1 over 2 and -1 over 2. To determine the value of j, there are two ways to combine the L and S, where vector summations and summations of the z components can be applied. So we shall consider the summations of the z component, which involve the orbital angular momentum quantum number with reference to z-axis and the spin quantum number with reference to the z-axis. The total of these two parameters will give us the total angular momentum quantum number with reference to the z-axis Jz. So just now we have found that one electron in p orbital, we have the L equals to 1 and Lz is +1, 0 and -1. Similarly, for S equals to 1 over 2 because we have only one electron, while the Sz equals to +1 over 2 and -1 over 2. And in order to find out the Jz, so we find out the Lz plus Sz. So Lz1 plus 1 over 2 of the Sz, we will have this piece of expression, and then 1 minus 1 over 2, we will have this piece of expression. Then next we have the 0 plus 1 over 2, 0 minus 1 over 2, minus 1 plus 1 over 2, and -1 minus 1 over 2. Therefore, we have 6 combinations of Jz, which are listed here. There are 6 components of Jz. The maximum value of Jz is 3 over 2, and we know that Jz is ranged from positive J until negative J. So, one of the value is Jz, 3 over 2, and the next value is minus 3 over 2. And in between 3 over 2 and minus 3 over 2, we have the j minus 1 here. So 3 over 2 minus 1, we will get 1 over 2. And then 1 over 2 minus 1, we will get minus 1 over 2. That means this range of the Jz, 3 over 2, 1 over 2, minus 1 over 2, and minus 3 over 2, they are belongs to the value of J, which is 3 over 2. And now we left the other two Jz, 1 over 2 and minus 1 over 2. So these two values here, they are belongs to the J value equals to 1 over 2. If you have j equals to 1 over 2, then the value of possible Jz is plus 1 over 2 and minus 1 over 2. So we have found the value of j, which are j equals to 3 over 2 and j equals to 1 over 2. Therefore, we have the one electron in p orbital will give rise to two electronic levels, which are doublet p 1 over 2. Doublet is come from the multiplicity. P is come from the orbital angular momentum quantum number where the electron occupied. And 1 over 2 subscript is the value of J. In addition to doublet P 1 over 2, we have another term symbol which is the doublet P 3 over 2. So these are the two term symbols that can be derived from one electron occupied p orbital. And we also can find out how many microstates are there through the equations given here, where it is 2s plus 1 multiply 2l plus 1. So there are a total of 6 microstates. So how to get these 6 microstates? Just like we have the Lz equals to plus 1, 0 and minus 1, whereby one electron, the spin quantum number with reference to z-axis is plus 1 over 2, or we call it as the spin up, and then minus 1 over 2 spin down. So if the electron is occupying in the spin up manner and in the orbital of Lz equals to plus 1, Therefore, the Jz is plus 3 over 2. If the electron is occupied, the Lz equals to 0, and with the spin up, then the Jz is plus 1 over 2, and so on. Therefore, we have 6 different ways that this one electron can occupy the p orbital. So we also call it as the 6th quantum state. And we have 6 wave functions associated with these two p term symbol. So this will show you how does the one electron occupy the p orbital with spin up and spin down with their respective Lz value plus 1, 0, minus 1, and Sz value spin up plus half and spin down minus half, together with the Jz value. The value is come from the Lz plus Sz. So these are the respective Jz value. So when we group them, we have the 3 over 2 positive minus 3 over 2. Then the next value is positive 1 over 2 and minus 1 over 2. So these four will have the same energy, and it is given with the term symbol of doublet P 3 over 2, whereby the leftover one, which is the 1 over 2 plus and minus 1 over 2, they have the same energy, or we call it as the degenerate. So they have the term symbol of double P 1 over 2. Okay. There is another way to determine the value of J, which involve the summations to find out the maximum, and also the difference between the L and S to find out the minimum. So for example, what we have seen just now, when we have one electron in p orbital, the maximum value of J equals to 1 plus half, which is 3 over 2, because L is equals to 1 and S is equals to 1 over 2, and another value which is involved the minimum value of J, it can be quantified using the L minus S, which is 1 minus 1 over 2. So you will get 1 over 2 as the minimum value. Sometimes we will have the situations whereby the maximum value and minimum value is with some distance apart, then we have to minus L plus S minus 1 and get the middle values until it comes to the minimum value. So the total electronic angular momentum is different in magnitude, where two different energy states depending on whether L and S is reinforced or opposed. So this is the reinforced, while we have the conditions where it is opposed. So the spin-orbit coupling results in the splitting of the energy levels. So later on in the next slide, what does it mean by splitting of the energy levels? And these informations can be used to label the state arising from the spin-orbit coupling of an electron in the various orbitals. The energy splitting of atomic term in the one electron in p configurations can be illustrated using the energy diagrams here, where initially we have only one electron in p orbital, so we do not know what is their respective energy when just one electron staying in the orbital. After that, we consider the effect of the multiplicity, so we have the term of doublet P. The doublet P term can be further split into their respective energy levels after considered the spin-orbit coupling effect. So we have the doublet P 1 over 2 and doublet P 3 over 2. In this example, the spin-orbit coupling of J value 1 over 2 is lower in energy compared to 3 over 2. So if the subshell is less than half filled, like in this example, one electron in p orbital, so the orbital p is less than half filled, then the level with the lowest value of J lies lowest. But if the subshell is more than half filled, then the level with the highest value of J will lies lowest. Okay, so that is how we determine the value of energy, the level of the energy for each of the term. And this state here is the effect of the magnetic field. If the atom is exposed to the magnetic field, then the levels with the same value of L and S and J, but it will be different in the value of Mj. Therefore, there will be splitted further. From WP 1 over 2 will be splitted into WP 1 over 2, which is minus 1 over 2 and plus 1 over 2. So it can be further splitted. Wow. Just now we have already seen that the degeneracy of a term symbols can also be determined where it is equals to 2j plus 1. And here are the other two examples with one electron in d orbital and one electron in s orbital. What are their respective term symbols? If we have only one electron in d orbital, the value of the orbital angular momentum quantum number L for d orbital is equals to 2. And the spin quantum number for one electron is 1 over 2. So we can find out the value of the J, where we have the maximum value of J with L plus S and minimum value of J, which is L minus S. So there are two levels in the configurations. With the d orbital, then the term symbols, the state symbol is capital letter D, and the multiplicity 2s plus 1 equals to 2. So we have the term symbol of doublet D, 5 over 2 and 3 over 2. While for one electron in s orbital, it has the orbital angular momentum quantum number L equals to 0, and the state symbol is capital letter S. Therefore, we have the term symbol with state symbol of capital letter S and only one electron, so the spin quantum number equals to 1 over 2. The J value, for the maximum value of J, it is equals to L plus S, so the value is 1 over 2. We do not consider the L minus S because if we have the L minus S, then the J will be a negative value. We have to take note that the value of quantum number can only has the positive value or the positive integer. Therefore, one electron in s orbital only have one level, which is doublet S 1 over 2. With the knowledge of the term symbols, and it can explain the fine structure for the hydrogen atom spectrum. So the appearance of the fine structure in the spectrum is due to the presence of different energy levels. We know that hydrogen has only one electron. Therefore, the splitting observed for the hydrogen is doublet. During the process of transitions, the selection rules for the electron, it can have the transitions with the change of principal quantum number with any value, while the change of the orbital angular momentum quantum number is limited to either increase by 1 or decrease by 1, and the total electronic angular momentum quantum number change allowed is either +1, -1, or no changes. So this indicates that the transitions between the S level and P level are allowed. Therefore, the transitions from doublet S 1 over 2 to doublet P 1 over 2 is allowed with delta J equals to 0, or from doublet S 1 over 2 to doublet P 3 over 2 is also allowed with delta J equals to 1 over 2 and delta L equals to 1. The transitions of the electron in the hydrogen atom, it can be further illustrated in this energy level diagram. So initially we have one electron in the s orbital. The term symbol is doublet S 1 over 2. When this electron is excited, it can be landed on any of the principal quantum level with the p orbital. So we can have the 2p with one electron. The electron from the 1s can landed at 3p or 4p. And due to the effect of spin-orbit coupling, the p orbital is splitted into two different levels, which is doublet P 1 over 2 and doublet P 3 over 2. So meaning that this electron here, it can come to doublet P 1 over 2, or the electron from the 1s orbital can landed at doublet P 3 over 2. So this will result in the appearance of two spectral lines in the spectrum. So we have the one electron in the s orbital, and it was excited to either doublet P 1 over 2 or doublet P 3 over 2. The electron will relax back to the ground state by emit the radiations. Therefore, the radiations detected by the detector will show the spectrum at the positions on this line and this line corresponding to the energy emitted by the electron when it is deactivate to the ground state from either doublet P 3 over 2 or doublet P 1 over 2. So there are two spectral lines are observed when the p electron of an electronically excited alkaline metal atom undergoes a transition and falls into a lower s orbital. One line is due to the transitions of the electron from the J equals to 3 over 2 level, and the other one is due to the transition starting in the J equals to 1 over 2 levels. So the splitting, the distance between these two lines is approximately 17 wave number, which also reflect the energy difference between these two levels is about 17 wave number.